Hi, this is an example problem from Chapter 24 on radio waves, a type of electromagnetic radiation. Pause for a moment so you can read the question. All right, so in this question, first thing we're going to do is we're going to try to figure out how to tune a capacitor so that we can get a radio station tuned on our radio. Well, first thing we note is that the frequency of the wave that we're trying to tune is 106.7 megahertz. So we can write that down right below here. Frequency 106.7 mega 10 to the 6th hertz, and a hertz we also know is 1 over a second. Let's look for a second just a little bit about electromagnetic waves. So electromagnetic waves is an oscillating electric and magnetic field. You can kind of see it here in this picture here. And we learned that when you have a changing magnetic field, you generate a EMF. Well, that EMF is associated with an electric field. So changing magnetic fields create electric fields, and vice versa. Maxwell showed that changing electric fields create magnetic fields. So as these two fields are changing and oscillating, they continually create one another, and they propagate along at the speed of light. And so like this is just a beam of light along this direction, propagating in the direction of the red arrow, because the vectors, the E and B, they only exist at the on the line where they begin, whereas the length of the arrow tells you the magnitude of them. Now, we can think of detecting electromagnetic waves in two different ways. So if we want to look at the magnetic field, well, notice that the magnetic field here is going to be oscillating back and forth, right? And as it goes through this loop, there's a normal line there, the changing magnetic field is going to induce an EMF, which creates an induced current inside the loop, and we can detect that. Similarly, if you have an oscillating electric field, if you use a dipole antenna, this kind of thing, it's going to have an electric field that moves up and down and changes direction back and forth. That's going to drive a current flow in the antenna due to the electric force on charges, and that'll also create a current. Now, we only are going to detect a strong value of current if this RLC circuit is tuned to resonance. So you can see we've got the L, the C, and just because this is a circuit made of wires, there's some resistance in there as well. So we've got an RLC circuit. We need to tune it so that the frequency will be correct to drive a strong current at the resonant frequency of this wave in the circuit. We'll recall back from chapter 23, we have an equation here. The resonant frequency for an RLC circuit is equal to 1 divided by 2 pi times the square root of the inductance times the capacitance. Now, in this problem, we know a lot of stuff here. We know what the inductance is equal to, and we know what the frequency is equal to. We got to figure out the capacitance. So a little bit of algebra here. Let's square both sides. That's going to give us resonant frequency squared is equal to 1 divided by 4 pi squared times L. And finally, to solve for C, we can go ahead and multiply both sides of this equation by C and divide by the frequency squared. So cancel these guys out. We're left with C. And so this is going to give us the capacitance is going to be equal to 1 divided by 4 pi squared L times the frequency squared. And then we just need to put our numbers into that formula. The inductance, 100 microhenry. And the frequency, squared. That comes out to a capacitance of 2.22 times 10 to the minus 14th farads. All right, for part B, it says, what is the wavelength of the wave that is broadcasting at 106.7 megahertz? So kind of going back to this picture here, you could see a full wavelength would be going from the start of the wave to where it starts again. So from here to here, that's one wavelength. And we can go ahead and calculate that over here. What is the wavelength being broadcast here? Well, we can use the good old equation that relates speed, in this case the speed of light, is the traveling speed of the electromagnetic wave, is equal to the wavelength of that wave times the frequency of that wave. And we want to calculate the wavelength. So wavelength is going to be equal to the speed of light divided by the frequency. So the speed of light, 3 times 10 to the 8th meters per second, divided by the frequency, which we just solved for, or we didn't solve for, we're given that. It's 106.7 times 10 to the 6th, 1 over seconds. So your seconds are going to cancel out here. We'll be left with a length, and that comes out to 2.81 meters. And so this is within the spectrum of radio waves. You yourself are probably 1.5 to 2 meters tall. And so this is, a wavelength. If you're looking at this picture here, right, this is, this length here. It's about, a little bit longer than the human body for radio waves. Stretches out over a good little stretch. All right, let's look at part C. How long does it take for the wave to travel from the broadcast station, a distance 5 kilometers away, to you? Well, we know how fast the wave is traveling, and we know how far it's going to travel. Question is, how long is that going to take? We can use a simple formula. Since the speed is constant, we can say speed is equal to distance divided by elapsed time, delta t. Now in this case, we are trying to figure out what is the time that it takes. So to solve for delta t, we're going to end up with this equation. The distance divided by the speed, and v here, that's equal to c for the speed of light. So let's go ahead and calculate what this time is going to be. The distance, 5 kilometers, but that is 5,000 meters. And the speed of light, 3 times 10 to the 8th meters per second. And we see that the meters will cancel. Well, we have 1 over the seconds in the denominator, which means we'll have seconds in the numerator. That comes to 1.67 times 10 to the minus 5th seconds. So as you already knew, the speed of light's extremely quick. To travel 5 kilometers takes about 17 microseconds. And finally, for part D, how many wavelengths will fit across the 5 kilometer distance? Well, in this case, we know what the wavelength is from part B. One wavelength is equal to 2.81 meters. How far is that going to stretch? Like, for example, in this picture, right? Here's a distance of 2 wavelengths, right? That's, 2.8 meters, about 5.6 meters or something, right? Here we got 5 kilometers. How many wavelengths are going to fit into that spot? Well, let's go ahead and figure it out. Starting with 5 kilometers or 5,000 meters, we can go ahead and use the wavelength as a conversion factor. And essentially we say, okay, so one wavelength is equal to 2.81 meters. How many wavelengths are we going to get in 5,000 meters? Well, we just got to go ahead and do this little bit of math here. 5,000 divided by 2.81 gives us 1,780 wavelengths. So if we stretched a light beam, or a radio wave beam, I should say, For 5 kilometers, you would have 1,780 individual wavelengths spanning that space.